Well, thanks a lot for the invitation, and thanks a lot to the organizers for putting together this very nice event. Thanks to Miriam and Jonathan in particular. And what I'm going to talk about is about the tameness of quantum field theory. And it's based on a number of papers. In particular, I want to highlight this work together with Mike Douglas and Lorenz Schlechter, who's a postdoc in Utrecht. And I will talk also a bit about this earlier work from the 2021, and at the very end, I will mention some work in progress. So what is the idea of this talk? I think many of us agree that having a finiteness principle could be a very unifying principle for many of the swampland conjectures, but maybe even for different parts of physics. If you think about black holes, for example. Now, such a statement is probably easy to make and much harder to put into practice. So what would be such a finiteness principle look like? So some concrete suggestions for a certain setting are finiteness swampland conjectures about effective theories. So here in these somewhat older papers, there was a discussion about the finiteness of effective theories arising out of string compactification. In this case, you have to put constraints on the extra dimensions, like there are compactification volumes and so on. So things are referring to string theory. While in this later version, one has a swampland conjecture which doesn't refer to string theory, but it says that if I fix some cutoff scale and I look at all effective theories which are valid at least below this scale, then this set of effective theories should be finite. What I want to do in this talk, however, I want to suggest something much broader than just this finiteness of these effective theories. Namely, I want to say that one should use tameness or O-minimality to use this as a finiteness principle in many physical situations, in particular in the swampland study. I will explain here. Okay, so what you will see is that these finiteness conjectures are implied, but it turns out to be a much broader concept. So which doesn't just apply to gravity, but it actually is already there in quantum field theories, but one has to be careful. Now, so what is tameness? So tameness is a generalized finiteness principle, but in a very clever way and in a very involved way in some sense. It starts very basic. It tells you, it restricts the sets and functions which you are allowed to use in formulating things. And you would call them tame sets and tame functions. It avoids wild functions and wild sets. So now you might be a little bit surprised what are wild sets, for example. For example, a wild set are integers and lattices. Okay, well, they are definitely infinite. So if this is a finiteness principle, then it should be avoided in this. And it also forbids complicated functions, like these oscillating functions, like the sine function, right? 1 over x. So this is a very wild function because like the dimension theory of this function doesn't even work out properly at 0. Where does it come from? Surprisingly, these ideas, they actually come from model theory. So they come from logic, from mathematical logic. And these tame geometries or this tameness principle actually is formalized in what one calls an O-minimal structure. So these O-minimal structures were invented by Finiteness to go around some of these logical undecidability problems. In fact, what we will see, the most basic O-minimal structures, they don't have undecidability. They have only decidable statements. And one of the reasons why this is true is that in Gödel's theorems about undecidability, they are always working over the integers. So if you somehow forbid the integers, you have better chances to be decidable. Of course, it's not quite as simple. Now, that's quite exciting, but it's still from the logical side. So now, why is there now so much interest in this subject? Well, actually, there is also a different point of view on the story, namely that these O-minimal structures, if you translate them into geometry, they formulate what Grothendieck envisioned as a mathematical framework for geometers. So essentially, the idea was if you do analysis, you come up with two wild things which never occur in nature, in the nature of a geometer. Yeah? And so he suggested there should be some Tame topology. And in fact, these O-minimal structures form precisely the such a Tame geometry. So Tameness is the theory of, or comes from the theory of O-minimal structures. A nice introductory book is by Finiteness. I encourage everyone who wants to learn about this to read this. It starts at the very basic level because it's also a very fundamental subject. If you want to learn more, there was last year, there have been many, many workshops, but in particular, there has been Fields Institute program for 6 months with hundreds of talks. So introductory lectures, but also many of the recent progress was reported there. Much of the recent progress. So now I have to define a little bit what I mean. So I first defined what is a structure, also sometimes called a model. A structure is a collection, and I look at the simple situation of subsets of Rn for n equals 1 to infinity. And I want to make it closed under some natural operations. So in set theories, I want to make this closed under finite unions, intersection, complements, and products. The important thing is finite, and in logic, that is something natural to do. So when I want to formulate a statement in a structure, I want that I can only use or and and not in finitely many times. Well, complements is obvious that you go back. Okay. Now, what is not so natural from the geometric perspective is, or maybe not as natural, is that you want to have this structure to be closed under projections. That's very important. And in logic, that means that you have the quantifier which there exists. There exists an X which has this and this property. So that's a projection property. And finally, we want to make it sufficiently rich, so we include polynomials. Yeah, so all zero sets of polynomials will be included in such a structure. Now, what is now the tameness condition? So what is kind of the special restriction on this structure? Because I'm struggling with this. Because this is also satisfied by all subsets of Rn, right? So the tameness condition is essentially the condition that the only subsets of the real lines are finite unions of points and intervals. These intervals can be infinitely long, but you should have just finitely many disconnected components. Now, the sets in an O-minimal structure are called Tame sets, and functions which have a graph being a Tame set of Tame functions. And then you have a Tame manifolds, Tame bundles, and so on. So you can develop a full Tame geometry. Okay? Just that you get some feeling, I quickly flashed one of the most basic theorems, namely a Tame function from the real line to the real line. You can always split the real line into finitely many intervals. And on these intervals, the function will be monotonic or constant. Yeah. What does this imply? That it implies that you have only finitely many minima and maxima, and then tame tail to infinity. So if you have a scalar potential, which is tame, it cannot have vacua when you go to infinity. At some point, there's no ups and downs anymore. Okay? So asymptotically, the function gets boring to some extent. Yes? What do you mean by it goes wrong? So so what you could try to do is you can try to formulate a projection. And once you project it down, like in the sine function, as we will see in a moment, any periodic function has infinitely many zeros or vacua, but then you project it down one dimension and then you get the integers. You get infinitely many points, but the integers are not a Tame set. Exactly. So indeed, that's exactly the property which propagates this finiteness condition from one dimensions to the higher dimensions. Okay. Now, so the point is that there are many O-minimal structures, but it's extremely hard to construct them. And the idea is to construct them is you have to single out the functions which are allowed to construct these sets in your structure. So as I mentioned, real polynomials I can use. So the zero sets of real polynomials, and if you complete them with the axioms, you get also inequalities. Then this is an O-minimal structure, which is called R-alge. But more generally, you can also introduce other functions, f1 to fn, and then form polynomial zero sets. And now the question is, what functions can I use here? That's the point. So you have just finitely many entries here, but which functions can I use without breaking this tameness axiom? Okay, and that's very complicated. So from a logic perspective, this is it means the following. I give you a set of symbols, namely, or set of operations, like I can multiply things, I can add them together finitely many times. So you don't have an infinite series or something like this. And then I add some number of functions which I'm allowed to use. And then the question is, which functions am I allowed to use in order to preserve this tameness axiom? Now, one of the big breakthroughs was in the field in the mid-90s that the exponential functions can be used. So while if I just use polynomials, I'm in algebraic geometry. If I can also use the exponential function, I have a much richer field. You can also add analytic functions, but only if you restrict them to some smaller region. And you can add both of them, the analytic function and the exponential function. And by the way, it's non-trivial to combine two structures into a new structure. So even if you combine things, tameness is by no means guaranteed. I give you another example, Pfaffian extensions. So you can add solutions to first order differential equations. First order differential equations are fine with tameness. Second order differential equations are not fine with tameness, because like the sine function, for example, satisfies second order differential equations. And yeah, and what I wanted to point out, which is hidden here, it's just hidden because there's still the chat going on. What I wanted to point out, only last year, a structure has been constructed which has the gamma function and the zeta function defined in it. So this is an active research field still today, like almost 30 years of research on constructing these structures. And it's very non-trivial to do that. So there has been much recent activity mapping out the tame parts of mathematics. Now, recently, much has moved into arithmetic geometry and now moving towards a number theory. Some recent proofs of deep mathematical conjectures. And we also contributed here in the sense that one of these finiteness theorems, which I gave before, finiteness conjectures, led to one of these general theorems about the finiteness of certain geometric objects. Okay, now let's move towards physics. So what is now the idea? The idea is we want to build a structure associated to a set of physical theory, to a space of physical theory. So how do we do that? Let's start with a set of quantum field theories. Say it's specified by a Lagrangian. Okay? And this Lagrangian can depend on the number of fields and some number of parameters. And then we also consider a set of Euclidean spacetimes, like here. And then we want to be both of these things to be definable in these structures. So when you think about this logic from a logic perspective is, I want to put enough functions into this structure such that I can formulate every equation which I want to use in order to define this Lagrangian, for example, or in order to define this Euclidean spacetime. So it is well understood what is a Tame geometry. So this is an easy task in this case. But for Lagrangians, it can be more difficult. To give you a feeling, if I just have a polynomial Lagrangian with real valued parameters, then, and some spacetimes, which are just our standard flat space or a torus or a sphere with the standard metric, then this is just the algebraic structure. So this is, that sounds very simple, but it's not quite true if you do that in practice, because there might be physical constraints on your parameters in the Lagrangian such that the theory is well defined. And this might require you to go beyond RH. Now, what is the next step? The next step is to add all the physical observables to this structure. So now I want to formulate statements about correlation functions in this structure. So I add them as functions to this structure. Now, of course, these correlation functions are very hard to compute, and the path integral and the operations in the path integrals are very likely never tame. They are actually very wild. But the basic idea is once you computed them and you regularized your theory and so on, the answer, the final answer, that should be tame. That's the idea, right? So we add them to the structure as functions. So they are complicated function on the space-time and on the parameter space. And this is a new structure then. And then we can, well, give you an example for the harmonic oscillator in quantum mechanics. You need the exponential to formulate the partition function, for example. Okay. And now, from a logic perspective, I highlighted this. You want to have a language which is rich enough to formulate all statements about your theory and your observable. And then you can ask the question, well, first of all, if I give you a parameter set which is tame, right, and a Lagrangian which is tame, are then all observables of the theory tame? So when does this happen, right? Then you can ask, what are simple conditions on the set of theories such that the space in which the theories are defined, the structure in which the theories are, is a tame structure? And this you can now do for all sorts of theories which we have. So you can do this for quantum field theory. You can do that for effective theories coming from quantum gravity. You can do that for CFTs, or you could do that for quantum gravity itself, whatever this is. So let me discuss this in somewhat more detail. How much time do I still have? Plenty. Okay. Very good. So then let me start with quantum field theories. So the first result which I want to tell you is that if you think about perturbative quantum field theories, you find quite a non-trivial theorem, namely that for any renormalizable quantum theory, where renormalizability is not so important at this point, with finitely many particles interactions, all finite Liouville amplitudes are tame functions actually in this O-minimal structure. And they are functions of the external momenta, the masses, and the coupling constant. So whenever I give you a finite loop amplitude, this is actually a tame function. This is not, if you pick all the possible function and you pick any of them, it's a very special set of functions which appear there. Okay. So there is some hidden finiteness properties in all Q of t amplitudes. And if I have the time, I will come later that there is even some sort of complexity interpretation. So why is this a non-trivial theorem? Well, it uses quite a deep understanding about Feynman amplitudes. First of all, it uses the fact that Feynman amplitudes can be associated with period integrals, with something very geometric. Now we are in the world of a geometer, and then the idea is that everything in geometry is somehow tame. But to show this is very non-trivial and has just recently been achieved in this paper, and in particular in this last one. Yeah, Vorti, yes.
Theorem has any meaning in the context of a non-originated?
Well, so you have to this theorem relies more on the usage of Feynman integrals. So as soon as you can define your Feynman integral as like in such a graph here, as an integral over some rational functions with certain sufficiently nice behavior, then you end up in this world. So the Lagrangian is not so important as if you can give me the Feynman integrals for the individual diagrams. Okay. Now, the important thing is everything has to be finite, any composition. That's why this is a finite loop amplitude. It's by no means clear that if all the finite loop amplitudes are tame, that the infinite series is also tame. Yeah. And we know that there are many issues there. There might be non-perturbative corrections, which make it then tame after addition. The theorem is very non-trivial. Actually, it has interesting implications for Feynman amplitudes. So essentially, symmetries and relations among amplitudes are actually deeply connected. And if you would have more time, some of these big recent breakthroughs are exactly about this. So they are about, if I have tame functions which involve exponentials, which are very transcendental functions, then if I have a relation, there must be some sort of symmetry dictating this. Yeah. So there are no special relations among the exponential functions which are a part of the usual one. Yeah. That would be interesting to investigate. So with string theory, it's a little bit tricky, right? String theory has infinitely many modes. And the question is, how do you think about these infinitely many poles of the amplitude? And we can talk about this afterwards. We also discussed this in our paper to some extent, but I don't discuss it. Okay, let's move on. So now you can ask, what about simple non-perturbative examples? I give you a list here without discussing them in any much detail. So where we know the answer and the setting is sufficiently simple, we can check tameness. And in fact, it turns out that each of these statements is non-trivial. So for each of them, you need a non-trivial theorem. Like here, for the harmonic oscillator, you need that the exponential function is a tame function, and so on. Here, you need that theta functions are tame on the fundamental domain. And here, you need that the periods are tame, which is something more recent. Now, the hope you could have is that, what about, maybe we can formulate general statements about zero-dimensional quantum field theory. So their gravity is not so important. So their tameness should be very general. And let's see what comes out here, okay? So the first thing what we did is we thought about phi to the 4 theory on a point, okay? Very simple theory. You compute the partition function, it's a Bessel function. And if you look now into our paper, you find there's no proof that this is a tame function. Actually, it satisfies the second order differential equation, and tameness has not been shown. So I gave recently a colloquium, and afterwards I received, I was very grateful to receive an email by Finiteness who said that, well, when he was thinking about tameness, he actually realized that there are certain structures, certain second order differential equations which produce tame function. And this Bessel function actually is exactly of this type. And in fact, it's actually tame in one of these Puffian structures, which have first order differential equation, but it's not tame in this very rich structure. So you need to go beyond this. And, now, what about Q of t on points in general? Well, then the path integral reduces to an ordinary integral. And it turns out that there's an old conjecture that if you have a tame function and you integrate it just with an ordinary integral, that you get again tame function, but probably in a richer structure. Yeah, that's a mathematics conjecture. It's just proved for some simple, not simple, but for some special cases. Unfortunately, these special cases do not apply to physics. They apply to perturbative physics, but if you want to do non-perturbative results, you have to integrate the exponential function. And integrating the exponential function is the tricky part. So, but if we take the mathematical conjecture to be true, then in fact, the physical observables in 0D, right, are tame functions of the parameters if we require that the Lagrangian or the action is actually tame function of the parameters and the fields. Okay, so actually the physics conjecture matches nicely or maps nicely to such a, the mathematics conjecture maps nicely to such a physics conjecture. So are all observables in all Q of T's tame? The answer is obviously not, right? So there must be something else. It's 0D, okay, but what about in higher dimension? Well, for example, if you have a discrete symmetry, which is of infinite dimension, then this can never produce a tame function. Right? There's nothing wrong in adding a cosine, for example, to a scalar potential in a normal quantum field theory. But this actually speaks very nicely to having no global symmetries in the theory, some quantum gravity conjecture. But that's not it. That's not the end of the story, right? Tameness is stronger than this. It also doesn't imply the absence fully of global symmetries, or it's not clear yet. But it's also not enough to get tame the absence of global. So you can have you can just pick non-tame potentials. I give you an example here. If alpha is irrational, then this also doesn't have a global symmetry. It never came out of string theory, but it's a non-tame function. You can also come up with very fancy potentials which have a vacuum locus, which are these infinite spirals. It never came out, something like this never came out of string theory, but in principle, you can write it down. If it would exist, it would actually give quite a challenge for the distance conjecture, because that, in this way, you could generate infinite distance points in compact spaces by putting an appropriate potential on it. Okay? And the most fancy example is probably this suggestion by Tachikawa, who wrote down a superpotential where the existence of supersymmetric vacua is undecidable. And in fact, you see immediately that it's non-tame. It has exactly the sign function, and it has exactly the reduction to the integers. Okay, so the Q of T's, our Q of T cannot be tame. So what about effective theories? Usually I'm a bit too slow. So for effective theories, you can now make a conjecture. So effective theories valid with quantum gravity, maybe they possess tameness. Okay? And this is part of this conjecture, right? It essentially says that the Lagrangians which come out of which you expect from effective theories compatible with quantum gravities are tame, and they have a tame parameter space and a tame field space. And this implies this finiteness conjectures, which I gave you before, because if the set of the set of effective theories would be infinite, then you would violate that the parameter space parameterizing them would be a tame space. Okay? It relates to some of the other conjectures. And what we did in this recent paper, actually, we suggested that also the observables in these effective theories are tame functions. If you put your cutoff, I mean, the important thing is the cutoff. Yeah, you need to make sure that you don't have infinitely many degrees of freedom in the field. And this brings me to the next part. Let's now look at RQ of t. And RQ of t, well, here at least you can hope that you have a better control about the set of theories. The set of Q of t's are reasonably well studied. They are axiomatically well defined CFTs. And so you can hope to eventually maybe prove one of these Tameness conjectures. And what we suggest in this paper is actually that Tame sets of CFTs have Tame observables. And what one could argue then is that the structure, the RCFT structure, is indeed O minimal if you start with a Tame set of CFTs. And rather remarkably, that has already quite some exciting implications, because that's now a quite powerful statement. It says it restricts every observable in your CFT. So if you think about observables in like using conformal partial waves become non-tame if you do certain things to them. For example, if you separate operator dimensions. If you want to forbid this, you have to make sure that you can never separate operator, generate gaps in your CFT if the operators interact. So there are quite interesting implications of this, because now tameness is a probe for every observable of the theory. Also, an old conjecture about the finite radius of convergence comes in here. Now, you can also ask, when is the set of CFTs tame? And there you have to bound your degree. You need to bound the thing which measures the degrees of freedom in the theory. Okay. So you have to bound the central charge and the lowest operator dimension in 2 dimensions. And in higher dimensions, we are not quite as sure if the conjecture is formulated precisely. What is clear is you have to appropriately bound the measure of degrees of freedom. So for example, in 4 dimensions, it would be A, right? Now, what we are not sure is what happens if you quotient out a symmetry to the set of theories. In 2 dimensions, we know that there are twisted states coming in and the gap goes smaller. It's not clear what happens actually in higher dimension. Maybe some extended object. Maybe it's clear to someone here. It was not clear. Well, we reached out to some of the experts, but there was no conclusion. So what we did is we said, in order that our conjecture has a chance to be true, we took out the gauges. But I'm pretty sure there are a stronger version. So it's challenging to provide evidence for this, and that took us quite some time to rule out some infinite families. Now, I have one more slide, if I'm allowed to do that. The outlook would be now to match this kind of tameness with actually some finiteness of complexity in the function. And let me, because I'm running out of time, just mention that, of course, if you have polynomials, there is just a finite amount of complexities in polynomials. Because you just to specify your set, you need just finite number of coefficients. And this is not true if you work with these huge structures, because if you have an analytic function, you can specify infinitely many free coefficients. And so you have some sort of infinite complexity. But rather remarkable, last year in the Mathematical Congress, it was suggested that there is a special set of O-minimal structures, which are known as sharply O-minimal structures, which have finite amount of complexity. And in fact, it's very natural that the tameness in physics actually should be related to this sharply O-minimal structure. Because then all your amplitudes, the set of theories should have a finite amount of complexity. This brings me to the end, and sorry for running over time. We suggested the tameness principle as a rather general principle. I just touched some of the subjects you can address with it. We found some interesting arguments in QFT, perturbative QFT, in effective field theories. We know from string theory, we know what's happening. But there's much left to be explored. well, implications of tameness, relations to other quantum gravity conjectures, and what we are now thinking about is relation to complexity and information. Thank you very much, and sorry for doing that.
Yes, if you give us the example of the business function, which is not paying our outland, so the structure we can name. Do you have any intuition how generalized phenomenon can be that if I give you a pointing which is, there's no signature acting on it, is it possible that there's going to be like a nice structure that includes all of nice functions?
No, so in fact, you can also write down functions which look tame and are not tame.
Sure, we can change the thing structure to be popular and something more general, but this general will not then become tame with respect to the new structure.
No, you can prove that there are such functions which are not tame. So it's by no means a simple criterion. And that's why also when you look at the solutions for this differential equation, it's very hard to say whether or not some solution is tame or not. And there's a lot of discussion about this limit cycles, for example, solving, say, the RG flow equation gives you some flows, and then you could have limit cycles. In mathematics, these limit cycles are actually also studied using structures and these methods. So, yeah, it's not simple.
I thought great. When you said that all observables are paying functions, you did a little bit more why, like what is the argument for that thing? You didn't get black.
Yeah. So what we did is, we looked at many examples, of course. Yeah, so like Leo theory and so on. And then we also looked at the partial wave expansion. And so in the partial wave expansion for two-dimensional CFTs, for example, you find hypergeometric functions. And these hypergeometric functions are also solutions to Picard-Fuchs systems. Picard-Fuchs systems are giving you periods, and then you end up in the tame world, at least for the space-time dependence. Now, the problematic thing is now the dependence on the operator dimensions. So you could say these are the parameters of the theory. And there it's not so clear that it's always tame. There you actually need to look at the specific CFTs. And what we found in specific examples, that the phenomenon which I described, that you separate operator dimensions, which are interacting operators, actually does not occur. Well, it's a conjecture, so feel free to disprove me, but it's quite exciting. So in this sense, this is the evidence which we present.
So if I give you a partition function, because we have gone over many selection factors, the selection factors can be labeled by the integer. How should I think about this notion of tameness there? Right? Because I would get an infinite sum over the integer to give you the answer. By your definition, it seems the partition function is what we get on the right hand, on the left-hand side, not framed. So it is something framed about the individual mode. If so, is there a statement about Fourier transforms?
There are also statements about Fourier transforms, but indeed, so this is one of the tricky part is always to say that when you have infinite sums over something. So if you have infinite sums over something, over some function, even if the individual pieces are tame, the answer might not be tame. But the statement what we make is essentially that you should not care about the way how you constructed your function, but you should look at the answer, the final expression for it. If it is a sum over infinitely many sectors, so be it. Many of these functions are like this.
So you said the Fourier transform is not framed by tameness.
So indeed, tameness is by no means easily well behaved under Fourier transform. So indeed, they are Yeah.
So it's really interesting that so many of our physical theories have been developed in this way that's captured by Tameness. And you look at a specific example. I guess my question is your vision of the Tameness conjecture that this principle of Tameness should be something that you can prove in a general class of physical theories, or maybe used as a mechanism to help define a quantum gravity theory? And if so, is there some sort of organizing principle in the sort of the deeper mathematics that makes this kind of a well-defined, coherent whole in one of the ways?
Yeah, so one exciting thing is that, of course, Tame structures, they are not necessarily filtered, in the sense that, as I mentioned, I cannot just throw in more and more function, but there is kind of a fascinating tree structure among them. So you can maybe take a function out and put another function in. So the question is, for example, maybe quantum gravity has a very simple Tame structure, and so it's maybe just R-Alch, just polynomial or something like this. And all the subsequent structures are like effective structures, which then get non-trivial functions because you do physical things with the original structure. And then you end up in all sorts of non-trivial or minimal fields. But of course, it's hard to develop a precise vision. But I think one of the things which is underappreciated is a little bit the fact that in string theory we deal with certain things which are integral quantized. Well, anyway, yeah. So I think this can shed quite a bit of new light on various aspects which we encounter in studying string theory vacua. Let me formulate. I would think it's a very fundamental property, actually. It's actually, because it's so basic, it's very fundamental in its formulation. So you can really see it as a logical property of your structure to have it in order to have certain things. Of course, you can ask, maybe it's decidability. That would be very nice, that every question in a physical theory should be fundamentally decidable, and so on. There are many papers on this in information theory and so on, but I don't know. But I'm very optimistic that it's an exciting property.
Nice talk with the intriguing connection to physics. I mean, maybe it's really one question. I'm still trying to understand the general general thought that we have, but to me, putting the context of a simple example, theory QFT.
Yes.
You're not claiming that all theory QFTs are things.
No,
right? And you're not saying they want to come up with one.
Well, yeah, interesting is such a. I see. Okay.
You did 5 to the 4 to the 5 to the 6 or 5 to the 8, whatever. And suppose one is not technical. You're not telling me that to go to that.
No. But I think what is the point of view on this is that, of course, our way of thinking about the universe is that maybe it just has finitely many states, right? So I think that there is some inherent finiteness property to everything which we somehow measure. So I would indeed say that it is eventually physically irrelevant, or in other words, it's an approximation to what one actually measures. So of course, I talk to condensed matter physicists and they say, oh, but I like the lattice. And then they compute in the lattice and they explain to me, well, I compute in the lattice because then I have a new symmetry. But they're also well aware that there is no lattice, an infinite lattice. So it's just an approximation to a very large system, so to say. And so what I think, what could be nice is to think that it's really very fundamental and that eventually this finiteness is something, so the actual theory are actually, the actual physical theories are Tame. Does it answer? So they are interesting as a tool, these other theories.
some immediate lattice, the well-defined physical structure, and of course, it's not realizable by this time you can start to know the actions of the fluid quantum system, and there's no problem with that. But of course, we know you cannot realize that it's a flat. The universe is finite, maybe because of quantum gravity, maybe because of this and that. Yes. So therefore, there are two different questions. One is the question of whether mathematical structure of the quantum system makes sense, and it does, even if it's finite. Absolutely. And they don't have that. But that's what I'm talking about. No. The Tameness is said about specific subclass of quantum theory, specific subclass of the quantum gravity theory. That's what I don't.
So you can use that as you can use it as a specific subset of quantum field theories. You can just pick it. That doesn't mean that the other quantum field theories are uninteresting necessarily.
But it's still a sense that it's quantum gravity. You're not saying, for example, the Tame one and the such one looking at quantum gravity, rising quantum gravity.
No, that's what I said in the conjecture. Yes, yeah.
You are.
Yeah.
So you are saying that the only theory that arises in quantum gravity are the Tame.
But once again, so with the lattice, for example, one has to be very careful. So when condensed matter physicists, of course, I know that you're careful. I'm just saying that when people think about, say, the Sine-Gordon model on an infinite lattice, they look at physical states which only are localized somehow. If you want to say, what are the undecidable properties on this infinite lattice? These undecidable properties are very likely not very interesting to a physicist, because you have to populate all the lattice points in order to end up in these logical inconsistencies. So physicists have learned to deal with the infinity in an appropriate way. It's just never, or it's not made necessarily very precise how to deal with it. Is that? No.
Okay, so Macaulay, and then for the last question.
Yeah, two comments that are probably naive. The first one is that mentioned conformity theory not staying in the class. And conformity theory also not to be considered by the bootstrap. And have you tried to combine it because the bootstrap all the space of range functions is much smaller?
We haven't tried, but it's certainly very interesting. So that's why we move towards the conformal field theory discussion, actually. Because what we want to do is, of course, it would be very nice to show a non-trivial Tameness theorem. And I think the technology is probably well enough developed to do that, say, in two-dimensional theories. But yeah, I'm not an expert in this conformal bootstrap story, so it would be very nice to team up, or if other people think about this.
You mentioned that the issue to Tameness arises from infinite size. Is the dependence of observables on expectation values of infinity? Is it Tame?
Yeah. So you could ask, what about like conformal boundaries or something like this? So our expectation, and we formulate this in the paper to some extent, is that also you have to put constraints on the allowed conformal boundary conditions. So Tameness is all about kind of what happens at singularity, for example. The singularities have to be sufficiently boring or not too wild. It's very hard to state in precise, apart from the way I did it, what exactly this is. Yeah.
Maybe one more quick question.
Yes, it's related to the possible point about that. Because you can, of course, make those lattice theories, but in that continuum limit, the comments will be like a even model. So, what is your statement?
Oh, yeah. Of course, yeah. So, but the interesting thing about Tameness is that it doesn't exclude infinite sets. Like the real line is a totally, absolutely fine Tame set. So it's kind of, there is a difference between having an infinite lattice and having a theory on a real line. So limits are not easy to handle. So yeah. So it's exactly the things which are always tricky are kind of also tricky here, right? So yeah.
Maybe, think about